Hello here from Kaiserslautern, Germany, and welcome to our presentation on the first results from the ML for Process Simulation project, which we are working on together with the Fraunhofer ITWM, the Leibniz Institut für Polymerforschung in Dresden, the German Research Center for Artificial Intelligence, and the Weierstrass Institute for Applied Analysis and Stochastics in Berlin. Today, after a quick introduction to the topic of fiber-reinforced polymers, I would like to present the project and objectives of the project ML for Process Simulation. And then, of course, as promised in the title, the results of the investigations on permeability in fiber structure with GeoDict, and based on this, the results of permeability prediction using neural networks. At last, I would like to give an outlook on the current and following work in ML for Process Simulation. First of all, I would like to give you all a short introduction into what this is all about. The context we are talking about is the manufacturing of fiber-reinforced polymers, more precisely the process group referred to as liquid composite molding. In LCM processes, everything starts with fiber materials, often in form of fabrics such as woven or non-crimp fabrics, which consists of fiber bundles. In the first process step, these brought into near net shape during so-called preforming, and these preforms are then impregnated with a low viscosity and therefore mostly thermoset resin material using injection or infusion. In a defined pressure and temperature cycle, this resin is cured so that we end up with our final component. The LCM process is used in a wide range of component sizes and variants. For example, small bicycle components of a few centimeters up to rotor blades of wind turbines with lengths over 70 meters. Different processes are used, such as high pressure resin transfer molding with pressures of over 100 bar, which is used in the production of the live module of the BMW i3. This contrasts, for example, with the vacuum infusion process used for the giant rotor blades, where the impregnation simply occurs from a pressure difference of around 1 bar from the vacuum to the atmospheric pressure. The flow of resin in the fiber structure is of course the core element of LCM and is commonly described by Darcy's law, which correlates the flow velocity of the resin on one side with the governing process parameters, here the pressure difference and the flow length, as well as the relevant material parameters. These are the viscosity of the resin system and the permeability of the fiber structure. So the permeability basically can be seen as the conductance of the fiber structure for fluid flow. And if you think back of the rotor blade with a pressure difference of 1 bar and long flow path, you can imagine that permeability is the crucial parameter for an efficient process. In addition, the knowledge is important for filling simulations of components, since incomplete impregnation leads to very expensive scrap parts. For precise filling simulations, the direction-dependent permeability must be determined for all textile configurations and deformations. However, the state-of-the-art in permeability determination is still experimental measurement, and only a few configurations can be considered due to the high effort. Numerical permeability prediction, on the other hand, offers high potential, as variations can potentially be considered easily and quickly. Nevertheless, there are still many challenges that have not been finally solved. One major challenge is the multi-scale structure of composites, ranging from the macro scale, the component level, to the micro scale with the individual fibers and even below. In the project Machine Learning for Simulation Intelligence and Composite Process Design, previous methods for numerical permeability determination will be brought together and developed further, thanks to the interdisciplinary expertise of the colleagues in the project in the fields of machine learning, mathematics, multi-scale simulations and composites. We hope to develop new approaches for the process simulation of composites using different machine learning approaches. And with Professor Advani and Professor Kurtz, we have very renowned experts in the fields of process simulation of composites and data-driven science at our side. The objective of the project is to focus on the impregnation of fiber structures at first, but in the end we aim to develop a general methodological expertise. The roadmap of the project is to first consider a simple plate tool, determining the permeability based on steady-state single-phase flow simulations. For the second stage, the physical complexity will be increased by performing permeability determination with transient dual-phase flow simulations. For this purpose, additional physical effects such as capillary forces have to be taken into account. In the third and fourth stage, the geometric complexity is increased first at the textile level and then at the component level, so that in the end we can investigate two-phase flow in a complex component from the macro to the micro scale level. All along the way, the costs and benefits of various machine learning approaches ranging from simple data-driven neural networks to complex physics-informed neural network-supported solvers will be evaluated and implemented. To go a little bit more into detail, I would like to explain the multiscale workflow as it is used today. First of all, everything starts at the macro scale level, where filling simulations are performed. The models are built from homogeneous elements, which therefore do not represent the material structure. However, these finite elements are assigned properties that represent the process or material behavior, such as the direction-dependent permeability. The local structure of the component thereby determines the configuration and deformation of the textile stack and therefore of the mesoscale model. And the structure of the mesoscale model in turn determines the structure of the microscale model. To build the models at the micro and mesoscale level, modeling parameters are determined from the datasheets, structural analysis based on microsections, or, for example, on computed tomographic 3D scans. Statistical representative volume elements are then generated. First, flow simulations are performed on the microscale level to predict the microscale permeability, and this microscale permeability is then assigned to the solid fiber bundles on the mesoscale level, since these are not fully dissolved down to the individual fibers due to the enormous effort that would be necessary for this. The permeability on mesoscale is then determined and used for the filling simulations on the macro scale level. Now we finally get to the results. We have performed extensive parameter studies with GeoDict to generate training data for the machine learning approaches and insights for modeling the fiber structure on the micro scale. We have more than 5,800 micromodels so far in the project, with a domain size of 320 voxels in each direction, a resolution of 0.5 microns, and each model configuration has been simulated 12 to 20 times. The models were varied in fiber diameter, fiber volume content, fiber orientation, fiber roundness, and fiber undulation, as you can see in the table. These two diagrams show part of the results at constant fiber roundness and undulation. On the left side are the results of permeability parallel to the fiber direction, and on the right side are the results transverse to the fiber direction. The fiber volume content and the fiber diameter were varied here. The fiber volume content between 50 and 66%, typical for LCM processes, and the fiber diameter between 6 and 12 microns. These are typical values that can be achieved with carbon or glass fiber. The points on the curve represents the mean value of 20 simulations. The results confirm the typical assumptions that a higher fiber volume content leads to lower permeability and that a larger fiber diameter results in higher permeability, since this normally results in larger flow channels. Here we have two more diagrams showing part of the data for the undulation variation. On the left side, results for flow in fiber direction, and on the right side for flow transverse to fiber direction at 56% fiber volume content for 3 fiber diameters, 6, 9 and 12 microns, and 4 different undulation parameters. Curved elliptical fibers were modeled with GeoDict FiberGeo. The segment length and the randomness parameters were varied. The results show that under these configurations, the fiber diameter has a higher influence on the permeability than the ondulation variations. In addition, it was noticed that the permeability results for all models with a segment length of 20 microns are almost the same, regardless of the randomness parameter. After showing you parts of the results, I would like to present the ideas of our machine learning approaches. First, again, the already known procedure for permeability determination, where we start with the input structure data, have our model, numerical computation, we have our velocity fields, and compute the permeability tensor. But now we want to completely replace the numerical simulation by a prediction for the microscale. Therefore, we have two different approaches. The first approach is to use only a few structural parameters as input and predict the permeability based on that. And I will present some results on this in a minute. The second approach is to use small models in binary form as input instead of just a few structural parameters. The much more complex approach is to use physics-informed neural networks to speed up the solver. Here the focus will be rather on the more computing-extensive mesoscale level. Of course, it has to be said that we hope for an acceleration, but it could well be that the effort is higher in the end. However, what is fast is the data-driven approach that I would like to present you now. The upcoming slides that I'm pleased to show you here were created by our colleague Dinesh Natarajan from DFKI, whom I'd like to thank very much for this. Before I come to the individual models, I would like to give some general information about the approach. The feed-forward neural network consists of an input layer, hidden layers, and an output layer. In order to make strategic use of the simulation data, it is divided into three subsets. We use 60% of the data as training data, 20% as validation data to check for overfitting during training, and the other 20% are used to evaluate the trained neural network at the end. During the training phase, the target values and the output are used to calculate the mean squared error. This error is used to update the learnable parameters of the neural network using backpropagation. This is how the neural network learns from the data. In modeling approach 1, the three input features, fiber volume content, fiber diameter, and fiber direction, are mapped to 9 target features using a feed-forward neural network. The 9 target features are the 9 components of the permeability tensor. The exact configuration of the neural network is shown in the table below, and this configuration is kept constant throughout the presentation for a fair comparison of the different approaches. As you can see in the table, the neural network has 5 hidden layers and 200 training epochs have been executed. On the right side, you can see the results obtained with the trained neural network with the 20% test data. The mean squared error was 0.0149, and the diagram depicts how well the predicted permeabilities match the ground truth permeabilities. On the x-axis are the ground truth permeabilities, the simulation results from the data set, and on the y-axis are the predicted permeabilities. The diagonal black line shows the ideal case r squared equal to 1. R squared values range between 0 and 1, and it can be interpreted as a share of variance of dependent variables that model is able to correctly reproduce. As you can see, the diagonal terms and cross-diagonal terms K12 are predicted with R squared scores above 0.85, whereas the K13 and K23 values are poorly predicted. This led to the question whether it is more effective to determine only the diagonal elements. Moreover, in the multiscale workflow, only the diagonal elements are passed on to the higher scale level anyway. Modeling approach 1a shows the results of the neural network where only the diagonal elements were used as output. Otherwise, all configurations remained the same. With this approach, a mean squared error of the test set of 0.0125 could be achieved. This is lower than before, but this could also be due to the fewer output features used to compute the mean squared error, 3 instead of 9. The R-squared scores in the diagonal permeabilities are improved by a negligible amount compared to the previous approach. Since this only led to a slight improvement, we followed the approach of using more input parameters to better describe the structure. This then led us to modeling approach 2. In this case, we have chosen 5 additional input parameters: volume fraction, surface area, curvature integral mean, curvature integral total, and Euler characteristics 26, which we have determined using GeoDict. Now we have 8 input features mapped to the 3 diagonal permeability values. With this approach, we achieved a slightly improved mean squared error of 0.0119 to 0.0125 for modeling approach 1A with the test data. So the additional input parameters seem to help in better predicting K11 and K22, but no improvement in predicting K33, as we can see from the R-squared values. In addition, we looked at another dataset where we varied the fiber curvature in the model. Now we used 2 additional parameters, curl segment length and curl randomness, as input for the feed-forward neural network. Again, we examined 2 approaches with different numbers of input parameters and choose only the diagonal terms as output. The mean squared error is higher than before, but it is not comparable as this is a different dataset. Considering the R-squared score, it is observed that the neural network is comparatively worse at predicting permeabilities compared to the previous dataset. The second approach here confirms that more input parameters help the neural network to improve performance. So to sum up, various simulation datasets have been created using GeoDict, varying different modeling parameters such as fiber diameter or fiber undulation. In total, over 5,800 microscale simulations have been performed so far. Based on this dataset, various machine learning approaches have already been investigated. This has led us to the following observations. The construction of appropriate input features is crucial to the performance of the neural network. The neural network is struggling to fit the K33, but depending on the use case, the output and target features can be modified to get better performance. The present work gives you an insight into the current work in the project. In addition, work is already underway on mesoscale simulations at IVW, on the conceptual design for the use case of physics-informed neural networks at the mesoscale at VIAS, on two-phase flow at the micro and mesoscale level at Fraunhofer ITWM, and of course further investigations on machine learning used at microscale level at DFKI. In addition, the IPF Dresden should not be forgotten, which provide important input parameters for the two-phase flow simulations. Last but not least, I would like to thank my colleagues for their contributions, the Leibniz Association for funding the project, and of course you for your attention. Thank you very much.